Okay. So I will fill you in. All right. So technically, if you have two conductors separated by an insulator, that forms a capacitor. So even if you have two charged particles and they are separated by air, you could say that that's a capacitor. And there's a certain amount of capacitance, which is the ratio of how much charge for a certain amount of electric potential difference across that. Okay. So we talked about doing this. I moved this slide over. Okay, so what I want you to do is determine the electric field in between the plates, considering that you have a charge of Q and positive Q, so positive Q, negative Q, and let's see what else I need to tell you. There's an area. The plate has a certain area. Yeah. That's what and it's uniformly, this surface is uniformly charged, like has a uniform charge density, surface area. Figure out the electric field.
Do you have any more of the equation sheet for this semester?
Welcome.
Do we need the distance between them?
We do not.
Okay.
Not for the electric field. I'll give you a hint. There's a Gaussian surface. So I'm going to call this area that A, just to make a distinction between the area of the plate and the area of the Gaussian surface. All right with that? Yep. So that's looking at that A. So I'm going to say electric field. It's constant. So I'm just doing that A, that area of the Gaussian surface. Okay. Is equal to the charge enclosed over epsilon naught. The charge enclosed, I'm going to say, is the surface charge density times this area, okay, over epsilon naught. So this is equal to surface charge density over epsilon naught, which is the same thing as a conductor, because it is a conductor. Okay with that? So, Toby?
What happens if you have like one plate that has like a -5 charge and the other one has like a +2 charge?
Great question. You wouldn't. You usually in this class, when they say capacitor, they're equally charged. But it's not impossible to like. Trying to think of a. I have an idea what's going to happen, but I'm trying to figure out a way to prove it. So let's say this is more positively charged than this is negatively. Actually, let's say this is more negatively charged because I don't like to drop protons. So what's going to happen is the excess electrons are going to be on this side. That's wrong. Yeah, okay, yes. Okay. Here's my definitive approach. Whatever the charge is on here, that's going to be the same charge on here, because if I draw my Gaussian surface like this, the Gaussian surface going that way is 0. Sorry, the flux going that way is 0. So that means the total enclosed charge here has to be 0. So whatever the charge is on this has to be the same charge on that. And whatever the remainder is out on here. We're going to assume it's going to be on this side rather than on these edges, because this is going to be really big compared to how thick it is. Okay with that?
So it's the same thing.
Yep. before I say yes to that, I want to think about that a while. But that's what would how the charges would be arranged. Okay, so if I look at the whole thing, I've got charge over area for surface charge density. Whole charge over the whole area of a plate. And so then I can substitute this Q over area, or epsilon naught times area. And this is the equation that you were given last year for the electric field and a capacitor. Okay. So seen that slide, seen that slide, you've seen that slide, that slide. Okay, so here, I want to calculate the capacitance. Okay, so we're going to go through this series. Like this procedure is going to be pretty popular. So you draw your Gaussian surface, figure out the electric field, calculate the electric potential difference, and then calculate capacitance. James.
On the AP test, is it going to be like stuff like that, where it's like part A, part B,
Yep.
or is it going to be just part A and C?
Nope. Part A, part B, part C. Okay. So we just did part 1 and 2. Part 3. Step 3. What we're going to do is kind of work backwards here. So electric potential difference is equal to integral, negative integral of V sub, we'll say S. I'm not really worried about the negative sign. Are you okay with me not worrying about the negative sign? And this is from, we're going to say from 0. Got another blue marker.
What?
Got another blue marker.
I do. You want another blue marker?
I would love another blue marker.
I'll bring you a blue marker.
Thanks, dude. Q over epsilon naught times A ds. D being the gap distance between these two. Charlie. It's just some vector that we can use in X or Y direction. Like here's S, X, Y. It's like the resultant. Just a
basically just like
yeah, it's an R, but it's not limited. S is more general than R. Thank you, sir.
you bet.
Okay. So now, what in here?
Man, I gave you a crappy blue marker. You're not even gonna write with it. Here's
I am.
the good one. Oh, I should have waited a little. This one doesn't do anything.
Lars! That's a good throw, Ruth.
Great, bro.
All right. So, what in here is changing? Nothing. The electric field in between here, these plates, is constant, regardless of how far you go away. Remember that? So, this just becomes, ooh, that's nice, times D. this, I don't know. It shouldn't. Get back down there. uh, okay. So that's the voltage across that, which is the same thing as this. It, it just becomes S, and then we plugged in D or zero, like D minus zero. Usually, what they're going to ask is, what's the electric potential difference across the plate? And you don't care about positive or negative. Okay, good with that? So,
What isn't the distance?
good question. So the question was, why doesn't the distance between uh, how far you are away matter? So this is this idea of an infinite plane of charge compared to an electron. So as you, so let's pretend I'm a negatively charged or a positively charged plate. So field's coming out this way from over here. It's going this way. This one's going this way, and they're going to cancel each other out in the x direction, but in the z direction or whatever this is, it's going to add up, and that's going to go on forever and ever and ever. And so as you go away from that, the parts of the plane that were so like near here, like that, their contribution was mostly this way, that it canceled out. But as you get further out, those further out ones have now more influence than they did, and so it just, that overall effect makes it constant.
So is the Q over epsilon A an approximation?
It's a pretty, in here, it's good. Here it's an approximation. You get with that? And this is for an electron. And so we always say, in an ideal sense, we don't have these fringe fields or like electric fields, like all the electric fields in the here and nothing's on the outside.
So is there like a distance that you can pull them apart? Like,
Get you on that.
you said you were talking about like infinite planes compared to an electron, but
Yep.
if you pull them far enough apart, wouldn't it like cease to
Yes.
be like an okay.
Yes. So the distance between these, it's like taking a capacitor is sort of like a fruit roll up.
Okay.
Okay. And the gap between those is the wax paper. Not very far. Well, good thing. Just kidding. Brandon, question. Do you have okay. All right. Good. So is this making sense? This progression here. All right. So the last thing we got to do is find the capacitance, and that's easy. That's just this ratio of charge over voltage. Well, we have some stuff. We've got the charge on a plate. We could say electric field times distance. That is a valid expression, but usually you don't stop there. Usually you go and do this. Charge over epsilon naught times area times distance. And so what you get is epsilon, the Q's go away, epsilon naught. A comes up on top now over distance. And that is the expression for capacitance of a parallel plate capacitor. Simon.
So where does the dielectric constant?
We'll get there. Okay, good with that. So this is what you were given last year. Okay, so I think I would explain this when I was doing the review, but with circuits, Ohm's law is kind of like the experimental way we can find the resistance of something. If we can measure the voltage and we can measure the current, we can figure out the resistance. Okay, this is a similar experimental way to find capacitance. We can measure the charge, we can measure the voltage across that, and calculate the capacitance. Okay, but in a resistor, you also have this equation: resistivity over length over area. This is the physical construct of what causes resistance. You have the certain characteristic of the material of the resistor times the length over the cross-sectional area. This is the geometry that defines the resistance. We can experimentally validate or like verify that with this, but this is what makes the resistance. This equation is what makes the capacitance. The physical construction, how big the area is and the gap distance between the two gives it a capacitance. We can measure that, we can verify that by measuring the charge and the voltage. Good? Okay, so that's where all that came from. That last year you had to memorize this, or at least it was on your equation sheet and you had no idea where it came from. And this, now you do. Okay. So let's talk about a spherical capacitor. Okay, strategy. The strategy is the same. Okay, so they are equally charged, positive and negative. Okay, I want to find the capacitance of this capacitor, and we are going to figure this out. So I'm going to draw my Gaussian surface in between these two spheres in the gap. Okay. So, and the inner shell is charged positive Q, the outer one's charged negative Q. I want you to figure out the electric field in that gap. Go. So your Gaussian surface is just going to be 4 pi r squared is equal to charge enclosed is the positively charged sphere on the inside over epsilon naught. So electric field is just 1 over 4 pi epsilon naught q over r squared. How'd we do? Toby.
Is dA always just the surface area of whatever shape you draw?
Yep. Well, so the line of charge, and then you did the cylinder,
Oh yeah.
it would not be the ends. It would be just the side. So the surface area of flux, the surface area of the object where the electric field is going perpendicular to that area. Okay. Step 2. I want to, Aiden,
Never mind.
you good?
Yeah.
Okay. Step 2 is we need to find electric potential difference. Do that. And let me make sure, where do you think we're going to put electric potential to be equal to 0? Electric potential, we're going to make 0 infinitely far away. Because like a point charge. So we're bringing it, we're starting, make sure you're starting from infinitely far away and bringing it in. Mm-hmm.
Why can't we like R where you start and you pull it out?
Use that when the infinity doesn't work. Now, that doesn't answer your question. Like, why doesn't this work? Um, it should.
The answer's different.
Is it? Oh, yes, it would be. Yeah. Uh, mm, to be 100% transparent, I've never understood why you can just arbitrarily, like with the line charge, like going from infinity coming in, that makes sense to me. The line charge, like, that didn't work. Let's do, that's always been like, that's okay. That's how you do it. All right. your electric potential going from infinity to, I'm going to say R, I'll just say big R. What is the electric field? If we did our Gaussian surface out here, what's the electric field out there? Tell your neighbor. Tell them why. Electric field is 0. Why? Closed charge is what? 0. You have a plus Q and a negative Q. They cancel each other out. So when we're going from infinitely far away, our electric field is 0. So that goes away. And then we go, and then from capital R to RB, it's still 0. Because the conductor on the outside, the electric potential is still whatever it is on the outside. Good with that? So then we are now at RB to R. And we have this expression for electric field. Over Q over R squared. And that becomes, oops, sorry, dr. That becomes, that's a 0. So your electric potential now is equal to 1 over 4 pi epsilon naught Q negative RB R, or R to the negative 2 dr. I'm going to take that and we'll just do that. We'll just leave that. That negative cancels with that negative, and then we're left with Q 4 pi epsilon naught times 1 over R minus 1 over RB. Yay! Play.
Why did we just skip over the shell, like, when calculating the, like, bringing it in?
Because the electric field is equal to 0. Sorry, let me do a better job with that. So infinity to capital R, electric field out there is 0. Good with that, outside the shell, because the total uncharged closed is 0. and then we are plussing a negative R to RB, but there's no change, there's no electric field in there, so that's still 0 in the conductor.
Oh, it's a conductor.
Mm-hmm. Yep. Toby.
Why don't you go from RB to RA?
Great question. So I want to know the strength of electric field at this location.
How do you know what R is?
Yep. Yep. And so if we take the whole thing going from here to here, I'm going to change this to A. You right with that? So your your voltage across that gap is going to be 1 over RA minus 1 over RB for the electric potential difference across those 2 points. Okay.
You get the same if you do it the other way.
Do you?
Yeah.
Okay. Okay, and then finally you say capacitance. This is the easiest part. It's charge over voltage, and your voltage is just what we got. And so I'd leave it like that, but if you wanted to go all out, you go. Oops. But
Why is it 0 from infinity to outer R again?
because the charge enclosed in our Gaussian surface, if we put it here, the charge enclosed is 0. So the electric field is 0 outside of that. Good there? Good times. When did I make your free response due? Such a softie. All right.
Yeah.
Might add to that. Make it due next week. That means test next week.
Yeah, that's average.
Okay? Good with that? Call that good for today. Foreshadowing. Capacitor looks like that.
So that's kind of like the derivation, right?
Yeah.